Before we get into the body of today's notes, I want to just take a moment to review quickly what we are doing up to this point. We're talking about dynamics, which is the study of why things move the way they do. And we started out by just really digging into Newton's laws, which are foundational to why things move the way they do. The first law says whatever the motion is, it wants to continue having that motion. Same speed, same direction. It's not going to change. If it's not moving, that's also not going to change. So inertia rules the land. Everything is going to keep doing what it is doing at this moment, unless it's acted on by an unbalanced force. And that's Newton's second law, saying an unbalanced force is going to cause acceleration in the direction of the force. And really the rest of this chapter now is about that cause and effect of forces acting on an object and the resulting acceleration that happens. And then of course the third law we're going to get into a little bit more in the next chapter. Now, to get back into Newton's second law, we're going to look at weight, which is a very specific application of Newton's second law. Before we actually use the formula for Newton's second law on weight, let's do a definition. This is my definition for it because it really works in what I say in class a lot, and so I want you folks to be familiar with it. The definition of weight is, it is the expression of gravity on an object's mass. Let me just get that down really quickly. Expression of gravity on an object's mass. And basically what that means is that instead of talking about gravity, and if I say, well, what is happening to this object? Why is it falling? And students are going to say, well, gravity. Or why is it that an object stays put on a desk? What force is acting on it? And they say gravity. And that's true, but gravity is universal. Gravity is everywhere. I want to know specifically for that object, why is it in a free fall? Why does it stay put on a desk? Because of its weight, which is the expression of gravity on that particular object. So very rarely do we talk about gravity. Mostly we talk about the expression of gravity, or how gravity expresses itself on individual things. And the way that it expresses itself is with the object's weight. Now let's look at F equals ma again. Here's the equation that we really are using as the bedrock equation of this chapter, and really of all physics, if you want to know, of all mechanical physics anyway. So how does this apply to weight? Well, the formula for weight is W is equal to mg, and you can see the correlation between those very clearly. Weight is a form of force. Force is a push or pull. Your mass is being pulled to the ground or being pulled to the center of the earth by your weight. It is the pull that causes you to fall in a free fall. Pull is a definition of, is what we use to define force. So weight is a kind of force. Mass is mass is mass. That doesn't change. And let's see, G, oh yeah, that's just acceleration due to gravity, which is what weight is, the expression of gravity on an object. So this formula really mirrors this formula very well. It just mirrors it in a very specific situation, how weight is going to affect the object's mass. So the formula we're going to use is W is equal to mg. And the nice thing is, because of the last chapter, you already know that g is either 9.81 meters per second squared, or g is equal to 32 feet per second squared. Simple application of F equals ma. Let's look at a couple of problems with this. The first one is calculate the weight of a 0.510 kilogram jar of Smucker's natural peanut butter. Not ordinary peanut butter, natural peanut butter. All right, let's write down what we know and what we don't know. We were given kilograms, and you know that kilogram is a unit of mass. It's not a unit of weight, it's a unit of mass, and its mass is 0.510. kilograms. I look at that unit and I say that's a good unit for what we're doing because my weight is going to be in newtons and kilogram is one of the component pieces of the newton. And I know that I'm looking for weight. So it feels like I don't have a whole lot going on, but I do know that for my formula for weight, I get to use g. And g is acceleration due to gravity, which is a constant. Now the only thing I have to do is decide, do I use 9.81 or 32? And because I'm in the metric system, I'm going to use 9.81 meters per second squared. I'm not sure why my equal sign looked like approximation signs. I don't know why it does that, but it's just an equal sign. There's nothing fancy or weird about that. They're just looking funny. W is equal to mg. Just plug it in. So W is equal to 0.510 times 9.81. And when I do the math on that, I end up with 5 kilograms meters per second squared. Kilograms times meters per second squared, which you know is the definition of a newton. So I'm allowed to use newton there. One more like this, and the other one is calculate the mass of an 80-pound bag of cement. So I know the weight, W is equal to 80 pounds, but what I don't know is the mass. I know that my formula is W is equal to mg, so I do know g because it is a universal constant in the imperial system. It's 32 feet per second squared. I look at all my units and I say, are those good? And I decide, yes, those are good, so I can go ahead and use them. W is equal to mg. So I'm going to plug in what I know and what I don't know. I know my weight is 80. I'm looking for my mass, and I know my acceleration is 32 feet per second squared. When I do the math, I find that my mass is equal to 2.5. And you remember the unit for mass in the imperial system is the slug. 32 feet per, so it is 2.5 slugs is the unit for my mass. Okay, pretty straightforward application of these, and they don't get really any harder than this. I'd like you please to do numbers 12 and 13 for your homework, and that'll be due on Thursday. All right, let's look at an actual or work through some applications of Newton's second law more broadly related than just weight. F equals ma can be used whenever there's multiple forces going on, and I can predict the consequence, the acceleration of those forces. Most problems have, and you're going to have to write small, I don't know why I didn't leave myself more room here. Most problems have several forces acting. And by the way, those forces that are acting are going to be acting in multiple directions. For example, let's say that I'm pulling a box up an incline. The forces are going to be, well, let's see, there's the pull of me pulling it up the incline, there's the weight of it going down, there's the force of contact because it's sliding on a surface, and, oh, let's throw friction in here for good measure. So now I have multiple forces, and they're all acting in different directions. So what we're going to have to do then is find a way to accommodate these. If they're all going in the same direction, you can just add them up. But they're not ever going to do that. They're going to go in various directions. So one thing we have to remember in order to find out these forces is we have to remember that force is a vector. And that creates a complication, but it's the reality. Force is a vector, and because it's a vector, you must use vector addition. You must use vector addition to find sigma F, the net force. Sigma F is the same as what we used to call the resultant. Sigma F is the net force. So if my equation, you don't have to write this down, if my equation is sigma F equals ma, the only way I can find the effect to this cause is to first find the net force, adding up all my forces. And the way that I add up all my forces is vector addition, like we did in chapter 1. And you guys are pretty good at that, so that's not going to really be that big of a problem. So how do you find acceleration? Well, let's see. If sigma F equals ma, then a, that's the then, sorry, A is equal to sigma F divided by m. So I can use this equation to find acceleration, but the sticky part is going to be finding sigma F. A principle that you need to know before we can get started with this is what I have written in number 2. You just have lines, so at some point just pause and copy what the notes are here, but I'm going to just go ahead and move on. The sum of the x components of all the forces, sigma F sub x, you've seen that before, acting on an object equals the product of its mass and acceleration on the x-plane. So the sum of the x forces creates x acceleration. Acceleration on the x-axis. The x forces create x acceleration. So now you're seeing that acceleration is also broken down into its two pieces, the x component of acceleration and the y component. So the x forces will produce x acceleration, and then similarly, the sum of the y components of all the forces acting on an object equals the product of its mass and acceleration on the y-plane. So all of the y components of the forces added up are going to create y acceleration, or acceleration on the y-plane. You'll have two different accelerations, or potentially you'll have two different components of acceleration going on, the x component of acceleration and the y component of acceleration, and you can bring those together through Pythagorean theorem, just like you can bring together the sigma f sub x and the sigma f sub y. Now, let's put this into an equation so it kind of makes a little bit more sense to you. So I have sigma f sub x is equal to f sub 1x, this is going to look familiar, plus f sub 2x, plus dot, 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 and now I'm not just finding sigma f sub x. In the past, that was all we did. But now that sum is equal to m a sub x. So my x, the sum of my x components of my force are going to create an x acceleration, or acceleration on the x-axis. Similarly, sigma f sub y is equal to f sub 1y plus f sub 2y plus dot, dot, dot is equal to m a sub y. It's just an application of sigma f equals m a, or a way of breaking it down into its component pieces so you actually can add f sub x and f sub y. You can add the forces up together. Now, what I'm going to have you guys do here is learn some steps to follow for doing these problems. And by the way, these steps are so important to keep you from getting bogged down in the minutia. You'll have so much data coming at you and you won't know what to do with it unless you follow a game plan that will get you out of the bog and get you onto solid ground. Follow these steps. It's going to help give you direction and keep you from going off on a wild goose chase, or just keep you from standing there saying, I don't know what to do. I just don't know what to do. Follow the steps. That's what you do. So the first thing you're going to do is you're going to make a drawing. And I'm going to say that with most of the times we have steps to follow. Make a drawing. And it's actually kind of important that you do that, because you need a place to attach my force diagram, which is next. You're going to construct a force diagram for that object you're interested in. So what you're doing is you're asking yourself what forces apply. So you're going to construct a force diagram by asking the 4 questions. Now, right now, you don't know what the 4 questions are, but you will. And these 4 questions are going to identify for you what forces are at play. And I'll just give you a little sneak peek. You're going to learn those 4 questions down there. So I've made a drawing, and I'm putting on the drawing a force diagram. It's kind of like I did before. I'm just going to give you a little quick look at what that's going to look like. So I had my box going up an incline. Okay, that's my drawing. And now I'm going to put on the drawing a force diagram, or it's also called a free body diagram, by the way, by asking myself the forces that are applied. Well, okay, is there weight? Yep. always. Is there tension on a rope or wire, push or pull? Yep. And that's why it's going up the hill. And then I'm going to ask myself, is it sliding or rolling or resting on a rigid surface? Yep. And my force of contact then, or normal force, is a part of it. And is there any conversation of friction? We're going to pretend in this problem there's a conversation of friction. So I'm going to do that. This is constructing the free body or the force diagram. I ask myself the 4 questions about forces, and do those forces exist there? And then I put those forces, of course, using arrows, that's what forces are. I put the arrows in my diagram to indicate what the forces are. Now I'm going to superimpose an XY axis, and I'm going to do that with this. So my XY axis, well, I should actually write it in for you, huh? Superimpose an XY axis. But here's the trick. Place one of the axes. I don't care which one you use. Usually it's going to be the x-axis, but place, oops, I have that in the wrong place, sorry. Place an axis on the line of motion. Now you're going to see why this is important later, but this is a trick to follow. If you want to make your life a lot easier, make one of the axes your line of motion. And let me show you what I mean in this one. So an XY axis is an imaginary thing. It doesn't exist in nature. And so because it's imaginary, there's a lot of flexibility with how you can manipulate an XY axis. As long as it's 90 degrees in between, the orientation of the X and the Y axis don't really matter. So what I'm going to do in this case is I'm going to make this my Y axis and this my X axis because it is in line with the line of motion. So I made my X axis the line of motion. I had to tilt it, but that's okay because you're going to find that that's going to make your work a lot easier if you do it that way. Then the next thing you're going to do is use your F equals ma in component form. You're going to use sigma F sub x is equal to the F sub 1x plus F sub 2x plus dot 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 is equal to ma sub x. And I'm also going to use sigma F sub y is equal to F sub 1y plus F sub 2y plus dot 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 is equal to m a sub y. And I'm going to substitute in what I know. I'm going to use those 2 equations, and by using those 2 equations, eventually I'm going to be able to solve for whatever my unknown is. This is very key here. Please make a big deal about this, and since I've discovered my highlighting tool here, let's go ahead and use that. I absolutely need you to know this. If, it's not supposed to be of, I'm sorry, if force works with motion, it is positive. If it works against motion, if it's a hindering force or it's an opposing force, it's negative. Regardless of the quadrant it is in your coordinate system. It doesn't matter what quadrant it's in. It's going to be negative only if it is a hindering force. It's going to be positive if it's a helping force. All right, please keep that in mind, and we'll be practicing those quite a bit. And I'm going to put this little remember in here. I see this happen sometimes, and I just want to put you on your guard not to think this way. Remember that an object's acceleration is the cause of force. It is not a force itself. It is not a force itself. It is the cause of force, not the force itself. I'm sorry, it is not the cause of force, it is the consequence of force. Did I say that before? Sorry. An object's acceleration is the consequence. Sorry about that. It's been a long day. It's actually now heading for 7 o'clock in the evening, and I'm running on an empty tank of gas, it feels like. An object's acceleration is the consequence of force, not a force itself. All right, now I'm going to break down those questions that you're supposed to ask when you're doing the construction. There are 4 questions. You ask yourself this question for every problem. Absolutely go through these questions. And if you do these questions faithfully, you won't miss forces. So the first question you're going to ask yourself, little letter A, is there weight? And by the way, the answer to this is always going to be yes. Because we do all of our problems here on Earth, there won't be a weightless system involved in this. Is there weight? Yes, every time. Every time the answer to that is going to be yes. And by the way, always vertical. There's going to be weight, and it's always going to be directed vertically. Notice that with that one drawing I did where the box was like this, doesn't matter that the box was on an incline. The weight is always vertical, always down. Little letter B, is there tension on a rope or wire, push or pull? And again, in the drawing that I did, or an outside push or pull. The one that I gave you, there was a rope attached to it that was pulling it up. So ask yourself, is there tension on a rope or wire or an outside push or pull? That's not always going to be yes. Sometimes it's going to be yes. And the next one is there force of contact? And the answer to that is going to be yes if the following is true. So it's going to be yes if, but only if this is true. If the object is on a surface, it's got to be a rigid surface. If the object is sliding or rolling or just moving on a rigid surface. It can even be sitting if we're, no, I don't want to say that yet. If an object is sliding, rolling, or moving, sorry, I need to write that in, or moving on a rigid surface. The answer is going to be no if the object is being raised or lowered. So it's really important here. No. If the object is being raised or lowered vertically. And let me talk to you then about this example that I gave you before. This is sliding along a rigid surface. There is going to be a force of contact here because it is sliding, rolling, resting, moving on a rigid surface. Now, being raised or lowered vertically, I don't mean there's a vertical component to it being raised up this hill. I mean literally it is being raised vertically or lowered vertically. And let's talk about, and I'm going to have to do this on the next page. Usually, force of contact is going to equal weight. When does force of contact equal weight? Force of contact equals weight because the force of contact is what you would think of as the floor pushing back. The weight is going down. If that's an unbalanced force, that is going to keep accelerating down. So something, if I have my object sitting on the floor, weight is going down. Unless it's balanced out by something else, Newton's second law says it's going to accelerate, and it's going to accelerate down. So something has to be balancing it out, and what's balancing it out is the force of contact, the pushback of the floor itself. And the pushback of the floor is really, we've talked about this before, it's really just the intermolecular forces that are tightening up and not allowing the box to go through the surface. So the force of contact is the force pushing back against the weight. Force of contact will equal weight when everything is horizontal, when the object is on a horizontal surface, and the push or pull is horizontal. So if I have a box here and I'm pulling it here, everything is horizontal. In this case, my force of contact is equal to weight. And you've got a little room on the side of your notes, especially if you have the ones that I've printed up for you. You have a little room in the margin. Please put this illustration in the margin. I just used up that space. So when is force of contact not equal to weight? It's going to be when the object is on a slant or the force is not horizontal, or both. All right, so at this point, we're really trying to accomplish two things here. First of all, is there force of contact? There's force of contact if an object is sliding or resting or rolling or moving in some way along a rigid surface. There is not force of contact if an object is being raised or lowered and it's not on a rigid surface like a trampoline. Okay, so then we're trying to identify, okay, if I have force of contact, is force of contact always going to be equal to weight? Because it looks like force of contact is just trying to compensate for weight. And in this case, that's exactly what it's doing. But it's not always going to be able to do that. Instead, sometimes it's not equal to weight, and it's not when the object is on a slant or the force is not horizontal. So for example, like I gave you before, this is my weight, and this is my force of contact. In this case, force of contact does not equal weight. Also, if I am pushing in this direction, I'm pushing down on my box to get it to move forward, then in this case, force of contact is not equal to weight. Here, you'll notice that it's horizontal, it's moving horizontal, and it's being pulled horizontal. That's why it's equal to weight. My motion is horizontal, but my push is not horizontal. So force of contact is not equal to weight. Again, let me say it never exists when it's vertical motion. And by vertical, I mean purely vertical, not up a slant. All right, and then the last question you asked. So the first question is there weight? The answer to that question is yes. Always for the problems that we'll be doing because they all take place on Earth. Second question, is there tension on a rope or wire, a push or pull? So you're going to look and see, is there something acting on my object through a rope or through pushing or through pulling or a wire? And then finally, then also is there force of contact, which we've defined the circumstances where there is force of contact. And then finally, my fourth question, and we won't get to this until later, but I want you to ask this every time so you get into the habit of asking it. The last question is there a discussion of friction? And I'm going to do one really quick application of this, and only the beginning of it, just so that you can see what this looks like, but we're not ready to move into, this has already been a long lesson today. We're not ready to move into actually working through a lot of these problems. So the four questions, is there weight? Yes, Always. Question number 2, is there tension on a rope or wire and outside push or pull? Got to look at the situation to see if that's yes or no. Number 3, is there force of contact? There's force of contact if it's rolling, sliding, resting, moving on a rigid surface. It's no if it's moving vertically. And then finally, the last question is there any discussion of friction? All right, let's look at the example 4.6, and I'm going to start this on the next page just because I don't have a lot of room to maneuver here. So let's look at 4.6. 4.6 says, a 63 kilogram roller skater is pulled by a rope that exerts on the skater a 50 Newton force in the horizontal direction. Ignore friction and calculate the skater's acceleration. So let me show you now how all of this gets put together. So the first thing I'm going to do is I need to do a drawing, and it's not going to be pretty, but we're going to make it happen anyway. So I have a skater, and this skater is on these roller skates, and he's on roller skates over here too. So he's on the roller skates, and he's on a rigid surface, and he's being pulled by a rope, and the rope is exerting 50 newtons of force. Okay, so I have my drawing. Now I'm going to do the force diagram. The force diagram is where my 4 questions come together. The first question is there weight? Yes, always. So I'm going to pull that down. Sorry. I am just messed up here. Let's go back to my albums. I don't want to do that. I have no idea what just happened here. There we go. Wow, I have no idea. So it's being pulled in this direction. We've already established that there's weight. Let's get that done first. You can tell I was distracted. There's weight. Now what they gave you was the mass. What you need to do is convert the mass to weight so that you can identify what the weight is going to be going down. So in this case, it is 63 kilograms is the mass, but at the same time, I'm going to put the weight down so that I have that to work with any time that it comes up. So the weight is going to be 63 times 9.81, which is, let me try that again, 63 times 9.81, and it ends up being 618 newtons. Okay, so I have my force going down, and notice I'm trying to pull them all together into one point. So is there weight? Yes, and I've already established what it was by doing W is equal to mg, and I'm going to put that right into my drawing so that I have the data there to look at both the mass and the weight. Is there tension on a rope or wire, push or pull? Yes, that's exactly what this is. There's a rope that's pulling on him, and it's pulling in the horizontal direction, 50 newtons. Is there force of contact? Is he rolling, sliding, resting on a rigid surface? Yes. So there's force of contact up here. And then finally, the last question, is there any conversation about friction? No. All right, so the next thing I'm going to do is I'm going to throw in my XY axis. I have to be careful about this. I'm going to throw in my XY axis. And everything then is going to be measured, the cosine and sine are all going to be measured against my XY axis. This one's pretty easy. I'm doing a simple one just to show you the process. So then the next thing is put it into the sigma f sub x and the sigma f sub y equation. So let's see what I know. I know that I have 3, and by the way, did you notice that I made the x-axis along the line of motion? I have 3 arrows. That means I have 3 forces that I have to add up. So it's going to be my W sub x plus T sub x plus F sub c sub x is equal to M A sub x. X is there because of the angle that it is. That's what makes it the X component, is how far away is it from the X axis. So now I'm going to do is plug that in, actually putting sine and cosine in. So the first one is going to be 618 cosine of 90. And hopefully you know that that's going to be 0. If not, let your calculator tell you that. Plus, and I'm making this positive because it's actually, not because it's on the positive x-axis, but because it is making the motion happen. It's not hindering motion, it's actually causing motion. So I'm making it positive, and I know that it's 50, and it's going to be cosine of 0 plus f sub c, which is my weight, and I could put that in there, but guess what? It's f sub c cosine of 90. I already know that that's going to be nothing, is equal to the mass, which is 63 a sub x. Now let's go ahead and add these up. Let's see, I've got 50, this is gone, I've got 50 cosine 0, which is 50, and I've got m a sub x. So my x component is equal to 0.794 meters per second squared. Again, these canceled out because they're cosine 90. They're 90 degrees away from the x-axis. Cosine of 90, 0. They cancel out. I don't have to deal with them. Now let's go ahead and figure out sigma f sub y. And you're going to see something really slick happen here, and you're going to say, my life just got way easier than I thought it was going to be. So sigma f sub y is equal to w sub y plus t sub y plus f sub c sub y is equal to m a sub y. But you'll notice all the motion is on which axis? It's on the x-axis. So what is the vertical component to my acceleration? Is he accelerating and bouncing up and down, or is he just accelerating in a horizontal direction? He's just accelerating in a horizontal direction, so a sub y is equal to 0. This is really a key idea here. There is no y component to my acceleration. He is accelerating strictly and entirely on the x-axis. So if that's the case, then my sigma f sub y is equal to m times 0. So my sigma f sub y is also equal to 0. The nice thing is I get to ignore all of that. So my a sub x is my acceleration. I have found the answer when I found a sub x. Now that's a lot to digest today. I'm not going to expect you to do any problems with this. You do have the weight problem.